Hi, welcome back. In this lecture, I would like to introduce boundary condition for open regions. So let's start this lecture giving you some motivation and why do we need open boundary conditions? Well, the FDTD method is often applied to microwave kind of problems, such as the calculation of radiation patterns from antennas or radar cross section, in short RCS. These problems involve so-called open regions. So what are open regions? Well, open regions are all those simulation regions for which the computational domain extends to infinity. So for instance, you see here an example. We have an antenna, we have electromagnetic wave propagating, and then we have a finite boundary condition that we want to enclose our computational domain. So the challenge that we're going to have is to implement such a boundary condition to mimic infinite domain, simulation domain. So as we know, it's not really feasible to discretize an infinite region. So something really not realistic. So we apply special boundary condition to terminate the computational region to mimic a potentially infinite region around our computational domain. The so-called open region boundary condition are also called absorbing boundary condition, or ABC in short. So how do they work? Well, so we mimic the infinite region by imposing an absorbing material around our simulation domain. So here in dark blue we have our simulation domain, and when we add around our simulation domain a number of cells that include an absorbing material. So we add a certain number of cells with given dielectric or conductivity or impedance, such that the material is capable of absorbing outgoing waves without actually reflecting any wave back. In this case, if we have one wave propagating in this direction, the system will allow to propagate through the absorbing material and with no reflection at the boundary. So this reflection won't be there. So the very trick that we're going to do is to design a material with the properties such that there is no reflection coming back into the simulation domain. The most common, the most famous, and the most used open region boundary condition is called perfectly matched layer, or PML in short. So this method was designed by Beranger by a seminal paper I will also post on the Canvas webpage. So what is the PML? Well, the PML is actually the extra absorbing material that we add around our simulation domain. So the PML is a layer of artificial material that surrounds the computational region. It is designed so that the waves propagating in the normal directions are damped, so they will lose their energy within the absorbing material. So the waves are sufficiently damped by the absorbing layer, so very little reflection will occur at the domain interface here. The absorbing material is finishing with the perfectly conductor boundary condition that we saw in the previous lecture. So the thicker is the absorbing material, the higher is the damping efficient. So the efficiency of absorption by the absorbing material is higher for thicker materials. Of course, increasing the absorbing material thickness also comes with a higher computational cost. So it's often a trade-off, between how much we want to reflect back and how much computation you want to include in our boundary condition. So let's look at the math and the basic idea of the PML. So in particular, we're going to look at what is the mechanism that enable us to avoid reflection at the boundary. So to mimic this infinite space, so-called open region. So the basic idea behind the method is to introduce an electric conductivity that we call sigma and magnetic conductivity that we call the sigma star in the absorbing material. So within our simulation material can be vacuum or can be the proper simulation and the proper material that we are using for our problem. And then we add an absorbing material with electric conductivity sigma and magnetic conductivity sigma star. So to do that, we introduce an extra term in the Ampere's law and in the Faraday's law. We had electric conductivity, so we have these extra terms, sigma multiplied by electric field, and then we have sigma star that is multiplied by h. So of course these equations are only solved within this material here. Right. So within our domain we keep the Maxwell equation, with the simulation, the electrics and the proper material coefficients. So we applied these equations within the boundary condition, and we have this special material that is sigma and sigma is characterized by sigma and sigma. So if you look at the theory about wave reflection and interface, is very convenient to introduce the concepts of wave impedance. And what we're going to do now is to look at wave impedance in the absorbing material that surround our simulation domain. So we define a wave impedance as the ratio of the transversal electric and magnetic fields for the artificial material. So in this case, the wave impedance is called the Z, right? And then we want to calculate the wave impedance for our absorbing material that we call the PML. So we can, from classical electromagnetics, we can get this formula that tells us that the impedance is this ratio here. So you see here the part, we have a part mu naught over epsilon naught, the square that is basically the wave impedance in the free space, so in case there is no material. Once you introduce the material with the magnetic conductivity sigma star and electric conductivity that is sigma, then we have this additional part at the numerator and denominator to take in account of the material. So we add sigma star over imaginary number multiplied by omega, and then we add to the denominator sigma over the imaginary number multiplied by omega. So we see that we basically we change the impedance of the wave in the free space by adding these extra terms that are characterize the medium of our PML. As I told you, so we want a special material that is not reflecting back any waves, so any electromagnetic waves. So what we want in principle is to let the wave going out smoothly without any reflection at the boundary. So we introduce a wave reflection coefficient that we call uppercase gamma naught, and this wave reflection coefficient is equal to the impedance in the free space minus the impedance in the PML divided by the free space impedance in this case, the addition with the sum of the impedance of our PML. So this is the equation here. So what we want to have in the case of the PML is to have this wave reflection coefficient equal to 0. And that's how we are going to design the material surrounding the simulation domain. So by going back to this equation here, as I told you, we want this reflection coefficient equal to 0. We know how these terms are built, so we can rearrange this formula here and find when this formula here is equal to 0, and we will find the formula here on the left. So what we found is that in case of sigma star over mu naught is equal to sigma over epsilon naught, then the reflection coefficient is going to be 0. So what we need to do is to take two conductivity coefficient such that sigma over sigma star is equal to mu naught over epsilon naught. So if you get the impedance on the PML equal to the free space impedance, so here there is no reflection at any frequency in there. So far we've been so this works nice and dandy for equations for waves that are exiting transversally the boundary condition. So for oblique incidence to the boundary condition is actually harder to avoid reflection. However, Béranger found a trick that is achieved through this very simple mechanism. So this simple mechanism is actually to split the electric field and the magnetic field into parts. So for example, if we have a x, and it is x component of the electric field, we split it up in two terms. In the two terms that contributed to the curl in the maximum equation. So in this case, we know the Ampere's law, and then we know there is also a curl including direction. So we split it up, the electric field according to the direction of the curl operator. And then we use a non-zero sigma and sigma star. Those are the conductivity in our PML, only for the derivative in direction normal to the absorbing layer. So let's see an example how this. So let's assume, for instance, that the PML has the PML where we want to apply our boundary condition as a z in the normal direction. So for instance, if we have a wall here, this is going to be the z direction. So let's see how this is going to work out. So what we're going to do is to split the two equations for ax and ay, are split in four equations. So instead of having only two equations for the two components, we split it up. Ax into more equation and ay into more equation. Right? So we're going to have this one for x and this one for ay. So important point that we note that we don't have the z, because az is not modified for the layer with the z as a normal. Important point when you see this that we split, we saw that the layer modifies the propagation only in the z direction, that is normal direction of the PML, and not in the tangential direction. As you can see here, we have the tangential direction ax, y that is not affected. However, the normal has this extra term that is considering the electrical conductivity in the z direction. The very same here in this equation here at the bottom. So therefore, no reflection occurs even for waves that are obliquely incident on the PML. So these are my last slides for this lecture, and talk to you soon.